Hello, this is part one of the Inductors and RL Circuits lab, the qualitative observations of a RL circuit. So I have, once again, my vernier circuit board, and we'll be wiring that up shortly. But there are a couple of things that are not built in on the circuit board, namely some inductors. And so I have a couple of sets of coils here that are used for various experiments. They will serve the purpose of an inductor. An inductor, after all, is essentially a coil of wire that's inserted into the circuit. And because both inductors and capacitors can store energy, capacitors store energy in electric fields and inductors store energy in magnetic fields, we want to compare and contrast the behavior of both of those in very similar circuits. So you'll see that the circuit we're trying to build is identical to the circuit we built back in the RC circuits lab, with the exception of we're replacing a capacitor with an inductor. But we're once again going to use our double throw switch. And so I'm going to go ahead and wire this up here. I'm going to go from the positive end of the battery to the top of my double throw switch. I'm going to then go from the output of that double throw switch, if it's in the upper orientation, to the pin on my lamp socket. I'm going to then go from the other side of that lamp socket to my inductor, and I'm just going to choose the smaller inductor first. Go from the other side of that inductor to the negative side of the battery. And finally, so we have that essentially discharge loop that we had in the capacitor circuit, I'm going to connect the other side of that double throw switch to that negative post of the battery. So if the battery's in the circuit, the loop goes from positive here down to the switch, through the light bulb, through the inductor, and back to the battery. When this switch is in the lower orientation, which it's in right now, the loop excludes the battery, and the loop is simply through the switch, through the light bulb, through the inductor, and then back to the switch. All right, so we have that all wired up, and I'm going to put a light bulb into the socket, power this on to 3 volts so that we're connected to the battery, and then flip the switch on. And the light bulb goes on. Not sure how visible that is on the video. We'll try, I guess we can see it that, okay. So the light bulb goes on relatively instantaneously here. And recall that when we did this in the capacitor lab, the light bulb was on, but then it dimmed out slowly over time. Here we don't see it dimming slowly over time. And so a first order guess at this point might be that the current in this circuit is relatively constant as a function of time. All right, we're going to try this now. I'm going to flip this off. Try this with the other inductor. So now I'm connected to the other inductor. I flip the switch on to connect the battery into the loop. And I observe nothing in the light bulb. Flip it off. Still nothing in the light bulb. And this ties into question 3 on the lab. Do inductors seem to have resistance? Well, you could actually measure the resistance of these inductors and find out that this inductor has a resistance of somewhere around 80 ohms. This small one has less than 1 ohm of resistance. So when the small one was in the loop, there was enough current flowing everywhere in the circuit so that the light bulb lit up enough that it would glow and we could see that. Now, with this larger inductor in the circuit, which gives us more resistance in the circuit, we're getting such a small current flowing in this circuit that we're not seeing any effect in the light bulb. And in fact, in neither of these experiments do we see behavior that parallels to the behavior of the capacitor. And there's some discussion in the lab handout about why that is. But this is the conclusion of this part of part 1. We're going to make a separate video of the FET simulator work for those of you who do not wish to do that part on your own in the simulator.